our last video for Chapter 2, we're going to be looking at nomenclature, so naming of compounds. We'll start with inorganic nomenclature, which organic nomenclature is something we're going to save for a later point in your life, but inorganic nomenclature is where we are naming compounds that are not primarily carbon and hydrogen. Once we get to carbon and hydrogen, the rules get a little bit more complicated, and like I said, we'll save that for a different course. But we're going to start with ionic compounds. If we've got an ionic compound, then the way that we name that ionic compound is to give the name of the cation first and the anion second. So we'll always do the positively charged particle first and the negatively charged particle second. If we've got a metal cation, and let's say that that metal cation always has the same charge. In other words, if that metal cation is one of the cations that is on this list, so either group 1 or group 2, aluminum, or these extra couple of transition metals that always have the same charge. Well, in that case, the metal is simply going to have the same name as, the ion is simply going to have the same name as the metal. The anion, we're just going to change the ending to "ide." And you probably are familiar with these, like oxygen is oxide, and fluorine is fluoride, and chlorine is chloride. So we just change the ending to "ide." All right, so let's look at number 59. These are all examples. These are all examples of metals that are on that special list. In other words, they're metals that do not have, or that always have the same charge. So, for example, sodium is in group 1, and since sodium is in group 1, it always has a +1 charge. So we're going to call this sodium chloride. Now, of course, you guys knew that is sodium chloride. But we got to start with something, right? So we start with one that you already know. This one, Mg, all right, well, magnesium is in group 2, so it always has a +2 charge. So that's simply going to be magnesium chloride. All right, here, calcium, so Ca, calcium is also in group 2. So it always has the same charge, is always +2. So this is simply calcium oxide. Next, Mg3N2, well, magnesium, as we saw previously, is always in group 2. Nitrogen, nitride is one of the ones that is on that list. And so we will have magnesium nitride. All right, Al, well, aluminum. Aluminum is a special one right here. It's always +3, so we don't need to worry about it having a special name. And then the other thing is sulfur. Sulfur is sulfide. It's always -2. So we'll come back over here. This is simply going to be aluminum sulfide. All right. If you grew up speaking British English, you would probably call this aluminium sulfide, and then for the F, you would probably have PH, because that's how the British spelling of it is. But here in the United States, we call it aluminum. I don't particularly care. In fact, I think mastering chemistry can handle both. All right, here we've got Li2O, and that is lithium. Lithium is in group 1, so it always has that same charge. And so we're going to call that lithium oxide. And then next, we've got calcium. And here our anion is hydrogen. And when hydrogen is an anion, we call it hydride. So normally hydrogen, we wouldn't call it hydride, but here it is. And then Ca, calcium, is in group 2. So that is simply going to be calcium hydride. All right. So there we go. That's problem number 59. Let's go back to the presentation here, and we'll look at some of our other rules. Metal cations that have more than one possible charge. In other words, ones that are not on this list, the ones that are blank spaces, so these other ones, all right, those we're going to use Roman numerals in parentheses immediately after the name of the element to indicate what the charge is. I will show you how to do that here on the next page. All right, there are some polyatomic cations that end in IUM, and you'll just name them like for example, ammonium is an example of that. So you'll just name it for the name of the polyatomic ion. The polyatomic anions have a fairly simple naming system, and it does require some memorization, but I'm going to show you how to do that. I will show you how to do that, kind of give you a primer on the systematic way that these are named. All right, so now for the metals that have more than one possible charge. So we're going to start with iron. If you recall, so iron, here is iron. Oh, here is iron. It is in the transition metals. It is not one of those special ones. So it's not scandium, it's not zinc, and it's not zinc, cadmium, or silver. So all of these other ones that are here, and including some of the ones that are down here like lead and bismuth, they can have more than one possible charge. So we need to figure out what the charge on iron is. So we'll go back to the presentation there. So the charge on that iron we can determine from context. All right, so we can determine that from the context. And so here I've got two different compounds of iron chloride, but they have very different properties, and so we want to make sure that we know the correct name. So here, the chloride, as we know, has a -1 charge, and with a -1 charge, and there's two of them, 2 times -1 gives us a total of -2 charge for the two chlorides. Well, that means that the total charge of that iron has to be +2. So this is iron 2 chloride. So that's iron 2 chloride. You'll notice that you put the parentheses immediately after the name, and in fact, there is no space in between that name and that open parentheses. And that's an unusual spacing thing, but that is the convention that we use in chemistry. And then we use the Roman numeral 2 to indicate that the iron has a +2 charge. Over here, we've got iron, and again, we've got 3 chlorides. The chlorides each are -1, so the iron here has to be +1, or +3 rather. And so therefore, that must be iron 3 chloride. So that must be iron 3 chloride. So now what we want to do is we want to switch over to our in-class assignment. Let me scroll down here a bit. Okay, so there is our in-class assignment. Oh, sorry about, I bumped into my microphone there. And here we want to name these. And it turns out all of these are examples of elements that were not on the special list, and so therefore have to have the Roman numeral to indicate what their charge is. So I purposely picked these, and in number 62, we're going to mix it up so that you'll have a combination of those. So Cu is copper, and copper can have more than one charge. Chloride is -1, and since there's only one of those chlorides, that means that this must be copper 1 chloride. So we'll put C, copper, parentheses, Roman numeral 1, chloride. Here we've got copper oxide. If we look, oxide is in group 6. Group 6 has a -2 charge, so -2, that means that our copper here must be +2. So we will call that copper 2 oxide. Next, we'll have iron oxide. And again, iron can have more than one charge. We know that oxide is -2. -2 times 3 gives us a total charge of -6. That means we must have +6 for the two irons. So that means each iron must have a charge of +3. So we will have iron 3 oxide. And just in case you're curious, this is rust. When you see some object and it's that, it's rusted, it's clearly rusted, that reddish brown color, that's iron 3 oxide. Very distinctive color. In fact, the surface of Mars is highly oxidized. It's got a lot of iron in it, so it looks rusty. All right, here we go. We've got PbO2. Well, oxide is -2, and -2 times 2 is -4. So that means that the Pb must have a charge of +4. And Pb is the element lead. So we will call that lead 4 oxide. So lead 4 oxide. Next, we have Pb3N2. So Pb3N2. Well, the nitride is -3. -3 times 2 is -6. That means the 3 irons must have a total charge of +6. So we'll divide by the 3 atoms. So +6 divided by 3 is +2. So this is lead 2 nitride. So lead 2 nitride. Next, we have Sn, and Sn is tin, so the element tin. F is fluoride. There's 2 of them. Each fluoride is -1. Remember, fluorine is in group 7, so it's -1. So -1 times 2 is -2. That means the tin must have a charge of +2. So we will put tin 2 fluoride. And then finally, Au is gold. We already know chloride's -1. There's 3 of them, so that means the gold has to have a charge of +3. And so that is gold 3 chloride. Gold 3 chloride. Interesting story in World War II. Interesting story about somebody who was escaping Nazi Germany and didn't want to carry his Nobel Prize, which was made of almost pure gold. Didn't want to carry his Nobel Prize because it would have been seized by the Nazis. And so what he did is he took the gold and he dissolved it in a combination of nitric acid and hydrochloric acid. That's about the only thing you can get to react with gold. And turned it into gold 3 chloride, put it in a jar, set it on a shelf for the remainder of the war. And then after the war, they reprecipitated the gold. And sent it to Stockholm. And Stockholm recast the Nobel Prize for him. Pretty cool story. I can't remember the name of the guy, but search up World War II Nobel Prize, and you'll probably find that story. Okay. So next, before we go to number 62, we need to go back to the in-class assignment and do a couple of things here. And that is, we need to look at polyatomic ions. So most of the polyatomic ions are anions, but some of them are cations. So some of them are cations, yes. And there is a list on eCampus that is called Polyatomic Ions List. And I happen to have this open here. Let me find it. There it is. So here is the polyatomic ions, and they're arranged by element. And what I want you to do is I want you to go through and memorize them. And I was looking at this earlier, and all of these look fine except for silicate. Silicate is supposed to be SiO4 4- charge. And for some reason, it's missing that 4- charge on there. Hopefully, future students will have the fixed version of this on eCampus. But if yours does not have that negative, you can just put that negative on there right now. And and fix that. But that is the list I want you to know. Now, if you want, let's go ahead and we'll look at, and really just memorize them. Make flashcards. Do whatever you have to get them memorized. All right, for polyatomic cations, there's a pretty limited list of polyatomic cations. There's the ammonium ion, which we will see numerous times. There's the hydronium ion, which we're not going to see named in compounds because, well, it just doesn't show up in a lot of situations in the compounds. But there's the hydronium ion. We'll talk about that in chapter 4. And then here we've got mercury 1. And it's weird because we have Hg2 2+. Why do we call it mercury 1? Well, there's 2 mercury atoms and the total charge is +2. That means the average charge on each mercury is +1. And that's why we call that mercury 1. So that one's kind of unusual. Now, most of the other ones that are on that list that I showed you are anions. And so here is a list of anions. If you're looking for a list to focus on for your first exam, I would look at this list. So I would take this list and focus on it first. So focus on this one first. But once you've learned these, then the remaining ones are really, really easy. So yeah, those remaining ones are quite easy once you've got these down. Now, there's a couple of simple, it's a systematic way of doing this, and a couple of simple rules that you can follow. If you have a set of oxyanions, and oxyanions are anions, so negatively charged particles, that have oxygen, one other element, and then some negative charge. Those are oxyanions. If there's 2 of them in a set, meaning you've got 2 of the same element other than oxygen and it's the same charge, then the naming is pretty simple. Whichever one has the fewer number of oxygens ends in "ite." The one with the greater number of oxygens ends in "ate." So NO2- is nitrite, NO3- is nitrate. SO3 2- is sulfite, whereas SO4 2- is sulfate. For PO3 3-, that's phosphite, and PO4 3- is phosphate. Now, what this doesn't do is it doesn't tell you what the number of the other atoms is. All it tells you is whichever one has fewer is "ite," and whichever one has more is "ate." So you still have to memorize them, and you still have to memorize the charges, but you'll want to, after you memorize those, then you'll want to kind of get them down so you know which one's "ite" and which one's "ate." It's pretty easy once you know that these are the 2 ions. If you have 4 oxyanions, and the example I'm going to give you is with chlorine, and so 4 oxyanions, the one with the fewest oxygen atoms, we're going to put the prefix hypo in front and end it in "ite." So ClO- is hypochlorite. We also have ClO2-, ClO3-, and ClO4-. The one with the second fewest oxygens, we're going to just end it in "ite." So no hypo in front of this one. So ClO2- is chlorite. The one with the second most oxygens, we're going to end in "ate." So ClO3 with a -1 charge, that is chlorate. And then if we sort of exaggerate this and go one more oxygen, then it's kind of a super-ate, and we instead of super, we just use per. So the most oxygen we're going to call per and then end it in "ate." So ClO4- becomes perchlorate, or perchlorate is sometimes how people say this. Now, you'll notice here it says also applies to bromine and iodine oxyanions. And I'm going to go back to that list of polyatomic ions I want you to know. And you'll see here are the ones we were just talking about. So hypochlorite, chlorite, chlorate, and perchlorate. But we also have hypobromite, bromite, bromate, and perbromate. Hypoiodite, iodite, iodate, and periodate. Once you've got 4 of these down, once you've got the chlorines, then the bromines and the iodines will be super easy to remember. So they will be super easy to remember. All right, so we want to look at numbers 62 and 63. And this takes a little bit of time on these. And the reason I want to take a little bit of time on these is because we've got polyatomic ions in here. We've got some of the metals need the Roman numeral and some of the metals don't. So we have to look at everything. Now, if you recognize what the ions are, then naming this is really, really easy. NH4, hopefully you'll recognize that pretty quickly. NH4 is ammonium, and the SO4 2- is sulfate, and so you have to have two of the NH4 pluses to balance out the sulfate, and so that becomes ammonium sulfate. All right. You'll notice that we don't have any of the prefixes like mono, di, tri. We're gonna see that in a different kind of nomenclature that we're doing a little bit later, but here we do not need to do that. So AlCl3, well, Al is aluminum. Aluminum is one of those that always has the same charge, and so it does not need a Roman numeral. So it's just aluminum, and then of course chloride is that. So we're just going to call that aluminum chloride. All right, next we've got Li, which is lithium. Lithium is in group 1. Group 1, it always has the same charge, so we don't need a Roman numeral. So that's lithium. And then PO4, that is phosphate. So this is simply lithium phosphate. So here is lithium phosphate. Next, we've got Ba. Ba is barium. I'm going to go back to the periodic table here. Barium is in group 2. Group 2 always has the same charge, so no Roman numeral needed. And barium is +2. And then ClO4, that is perchlorate. So this is simply barium perchlorate. Perchlorate. I nearly put "ite" there. So perchlorate. There is no perchlorite. So barium perchlorate. All right, here we've got copper. When we come over here and look at our periodic table, copper is not one that always has the same charge. Copper can have more than one possible charge. Therefore, we need to have the Roman numeral. NO3, that's nitrate. Nitrate has a -1 charge. Since it's -1 and there's two of them, the total charge is -2 for those two nitrates. That means that the charge on the copper has to be +2. So we're going to call that copper 2 nitrate. So copper 2 nitrate. Next, we have Fe, which is iron. Iron, again, is one of those that does not always have the same charge, so we have to use a Roman numeral with iron because iron can have more than one oxidation state. Our anion here is hydroxide. Hydroxide has a -1 charge, and with -1, and there's two of them, that means the iron must have a +2 charge. So this is iron 2 hydroxide. All right, next, calcium. Calcium is in group 2. Calcium always has the same charge. All right, so that's going to be calcium. And then here we've got C2H3O2, that's acetate. So this is simply going to become calcium acetate. And again, we do not need a Roman numeral because calcium always has the same charge. Cr, that's chromium. I'm going to pull the periodic table over again. Here's chromium. Chromium has more than one possible charge. Again, most of the things here in the transition metals do. So chromium has more than one possible charge, and so we need to figure out what the charge on that chromium is. If we look, we've got carbonate. Carbonate has a -2 charge. So carbonate is -2. There's 3 of them. So 3 times -2 is -6. So the total negative charge is -6. That means the total positive charge that we're going to get from the 2 chromiums is +6. And so positive 6 divided by 2 is going to be 3. So we will have chromium 3 carbonate. All right, and our next one, I kind of went over into the next box here, but no big deal. The next one is potassium. Potassium's in group 1, always has the same charge, so that means we do not need a Roman numeral. And then CrO4, 2-, that's called chromate. And if you don't know that, you'll just have to memorize that. So chromate, it is on your polyatomic ions list. So this is simply potassium chromate. There we go, potassium chromate. So now for number 63. On this one, we have the name, and we want to get the correct chemical formula. And so usually the way I recommend doing this is to go ahead and write the symbol with the charge. Sodium is in group 1, so it has a +1 charge. Phosphate, as you will eventually memorize, is PO4, 3-. Remember, when you're memorizing these, you need to have the correct number of atoms and the correct charge. So +1 and -3, that means that you're going to need 3 of these sodiums to match up with the 1 phosphate. And so our formula is simply going to be Na3PO4. So Na3PO4. You'll notice I almost accidentally put parentheses around that. You only need parentheses if you have more than one of a polyatomic ion, and we'll see that here in the next one here. Cobalt 2, so cobalt is CO, and that's 2+. Nitrate is NO3-. Since we have a +2 and a -1, we're going to need 2 of those nitrates, and so the formula is going to be CONO3 2. All right, next for barium. Barium is in group 2, so it's always +2. Bromate is BRO3-. And again, you will get that down eventually once you've worked on memorizing them. Since you have a +2 for barium and a -1 for the bromate, that means we're going to have 2 of those bromates, and so this is going to be BaBrO3 2, and that is barium bromate. Next, copper 2. Well, copper is Cu2+. Sulfate is SO4 2-. Since this is +2 and this is -2, we just need 1 of each, not anything complicated there. So it'll be CuSO4. So CuSO4. All right, potassium hydrogen carbonate. Potassium is +1, and then hydrogen carbonate is sometimes called bicarbonate, and that is HCO3-. Well, since potassium is +1 and the bicarbonate is -1, we're just going to need 1 of each, and it'll be KHCO3. Then finally here, we've got chromium 3 acetate. Well, chromium is Cr, and then of course, since it's 3, it's 3+. Acetate is C2H3O2-. We've got a +3 and a -1, so we will call this, or we will write this down as Cr. And since we have 3 of those, we're going to need to put in parentheses C2H3O2 and then a 3 to indicate that we've got 3 of those acetates. All right. So the next thing that we want to look at is acid nomenclature. With acid nomenclature, there are 3 kinds of acids that we want to write. So if we think of an acid as an anion where we've added hydrogen until it becomes neutral, then there's 3 types. There's the kind where the anion ends in "ide," the kind where the anion ends in "ate," and the kind where the anion ends in "ite." If the anion ends in "ide," for example, chloride, Then in order to get it to an acid, whatever the charge is, a -1 there, we're going to add 1 hydrogen to it in order to get HCl, and then we'll just simply change the "ide" to an "ic" and put an hydro out front. So for example, chloride becomes hydrochloric acid. Bromide becomes hydrobromic acid. And iodide becomes hydroiodic acid, which that is a lot of vowels in a row, but that is the case. So let's practice a few of those real quick, right? So HCl, and if we want to get the anion, well, just however many hydrogens that are there, remove that and increase the charge by -1. So that would be chloride, Cl-. Since that ends in ide, it's going to be hydroic. So hydrochloric acid is going to be the name. HF, again, that's fluoride, and so when we put that, we'll have hydro out front and change the ending to "ic." It'll be hydrofluoric acid. Bromide, so HBr, we remove the hydrogen, we get bromide, and so this will be hydrobromic acid. So hydrobromic acid. HI, remove the hydrogen, we'll get iodide, so this becomes hydroiodic acid. So again, just change that ending to "ic" and put hydro out front. H2S, we'll have to remove 2 hydrogens there. We will get sulfide. All right, so put a hydro out front, change the ending to "ic." And you might think it's going to be hydrosulfic, but it's not. It's hydrosulfuric acid. So all the rules, and there's always exceptions somewhere. All right, so hydrosulfuric acid. Here, if we remove the hydrogens here, we'll get oxide, and so this would, of course, become no, it's just water. It's just water. It's not hydroxylic acid. That would be weird. All right, so so it does not count as an acid, but these other ones, and there are a few others, and we'll see at least one of those on the in-class assignment here in just a couple of minutes. Now, if the anion doesn't end in ide, if it ends in ate or ite, then again, the rules are fairly simple. For ate, we just change the ending to "ic" and put the word acid afterwards. And so, for example, chlorate becomes chloric acid, and perchlorate becomes perchloric acid. Those are the 2 examples we've got in the box over here. So ate becomes "ic." All right. If your polyatomic anion ends in ite, then once you add the hydrogens and make it the acid, then you're going to change the ite to us and add the word acid afterwards. So hypochlorite, which would be just ClO-, becomes hypochlorous acid, and chlorite becomes chlorous acid. So ate becomes "ic" and ite becomes us. All right, to practice this, I'm going to go all the way back, when I was in high school. My high school chemistry teacher gave us the mnemonic, "I ate so much it made me sick." And of course, sick is misspelled, but then it means that it anyway. All right, so I ate so much it made me sick. So ate and "ic." There's not one for the ite. I ate so much it made me sus. No, that doesn't make any sense. But I ate so much it made me sick. That will work. So if we have an anion, carbonate, and we add 2 hydrogens, whatever the negative charge is, that's how many hydrogens we would add. We add the 2 hydrogens, we'll change the ate to "ic", and we will get carbonic acid. So H2CO3 is carbonic acid. So here is sulfate. If we add 2 hydrogens, we'll get H2SO4. And again, it might look like this should just be sulfic acid, but it's actually sulfuric acid. Carbonic acid, that is the acid that is, carbonic acid is the acid that is in carbonated water, and what makes sodas a little bit acidic. And sulfuric acid, that is battery acid. That's kind of fun, right? All right, sulfite, remember ite becomes us, so add the 2 hydrogens and it will be sulfurous acid. So H2SO3 is sulfurous acid. It's important that you know the difference between these two. Sulfuric acid is a strong acid. Sulfurous acid is a relatively weak acid. Next, we have nitrate 8 becomes ic, so that becomes nitric acid when we add the one hydrogen, whereas nitrite becomes nitrous acid. Very different acids, so these have very different properties. Here we've got phosphate. So phosphate, again, you would think, oh, I changed the ending to ic. Should it be phosphic? And that is not the case. It is phosphoric acid. So we do put the or back in there, but that's okay. So phosphoric acid is H3PO4. And then here we've got phosphite, and ite becomes us, so that becomes phosphorus acid. Phosphorus acid. Spelled differently than the word phosphorus, which is the name of the element. Phosphorus means it's the type of acid, H3PO3 is phosphorus acid. All right, acetate. So 8 becomes ic. That becomes acetic acid. That's the acid that is in vinegar when you if you have some vinegar. And then 8 perchlorate. 8 becomes ic. So this would become perchloric acid. Perchloric acid. All right, now we're going to go look at number 68 on the in-class assignment. So number 68. Switch over to that in-class assignment. All right, HF. All right, and then right next to it, I'm going to write F minus. So I'm going to remove the hydrogens. And we know F minus is called fluoride. So this, when it's ide, you put hydro out front. So this will be hydro fluoric acid. All right, H2S, and then I'm going to put S2 minus because once we remove the hydrogens, we'll have that. That is sulfide. We do the same thing here, so this will be hydrosulfuric acid. All right, hydrosulfuric acid and sulfuric acid are very different. Down here, this one is sulfuric acid. We'll go ahead and do this one. SO4 2 minus. That one's SO4 2 minus. And then here we've got, so H2SO4 is just sulfuric acid. Well, that prefix makes a huge difference. Sulfuric acid is battery acid. It's a strong acid. It will eat through clothing and damage your skin. Whereas H2S, hydrosulfuric acid, that is the odor of rotten egg smell. So those are very, very different. H2SO3, well, let's write this, SO3 2 minus. SO3 2 minus is sulfite. Ite becomes us. So this is sulfurous acid. All right, HC2H3O2. So C2H3O2 minus, that is acetate. 8 becomes ic. So this is acetic acid. And as I mentioned a little bit earlier, that is the acid that is in vinegar. Here, I should put this. So hydrofluoric, that one's poison. H2S, this one is rotten egg. That's the rotten egg smell is H2S. Sulfurous, there's not a common thing you'd use that for. Acetic, this is the acid in vinegar. All right. HNO3. All right. Well, NO3 minus, that is nitrate. Nitrate. 8 becomes ic, so that's nitric acid. All right. Nitric acid, that's some dangerous stuff. You got to stay away from the nitric acid. You get nitric acid on your skin, you don't necessarily know right away, but you will soon. And it will leave some pretty nasty stains and scars on your skin. All right, H3PO4, well, PO4 3 minus, that's phosphate. 8 becomes ic, so this is phosphoric acid. All right, next we have HCN. Remove the hydrogen, we get CN minus. CN minus is cyanide. Since it's an ide, even though it's technically not a binary acid, we name it like a binary acid. So we're going to call this one hydrocyanic. So cyanide becomes ic, so hydrocyanic acid. And this one is a deadly poison. Just a few milligrams, breathing that in, and you may not have another day. It's bad stuff. Hydrocyanic acid. All right, C2O4 2 minus. So HC2O4. Well, C2O4 is called oxalate. So that is called oxalate. And so this is called oxalic acid. So that is oxalate, and this is oxalic. All right, HClO3. We saw this one on the overhead a little earlier. So ClO3 minus, that is chlorate. 8 becomes ic. So this is chloric acid. That is chloric acid. All right, let's see. HBrO2. Well, BrO2 minus, that is bromite. Ite becomes us, so this is bromous acid. And then here we've got HiO4. IO4 is periodate. So 8 becomes ic, so it's periodic acid. Now, you may look at that and you may think, periodic, that looks like that should just be periodic acid, because it looks like the word periodic, like we have in periodic table. But this is properly pronounced periodic acid. Periodic acid. All right, so those are the names of those acids. Now, one thing, it is important to understand this because if you don't know the difference between these, you've got some major issues that are going to happen. These have very similar names. All right, so there's 5 different acids that have chlorine. This one is hydrochloric acid. This one is hypochlorous acid. This one is chlorous acid. That one is chloric acid. And that one is perchloric acid. And you don't want to confuse hydrochloric acid with chloric acid. Hydrochloric acid, that's muriatic acid. It's kind of like it is stomach acid, but it's used in a lot of different applications, and it's it's a strong acid, but relatively not too dangerous. But all of these other ones are quite strong oxidizing agents and will act as bleach. So you don't want to confuse these. These are a big deal. Okay, we're almost done. We're almost done with chapter 2. We have a little bit of stuff left, and so our last topic is going to be binary compounds, nomenclature for binary compounds. And these binary just means 2. So there's 2 elements, and most of these elements are going to contain nonmetals or perhaps a metalloid in a nonmetal. And so I'm going to go back over here. So mostly these binary compounds will contain either just the green things or some of the green things with some of these blue things. And if it's got the metals in it, use the ionic nomenclature. And if it doesn't, if it's just got these things in it, then you're pretty good. Now, I'm going to go back to this list, and then I'm going to come back over here because the very first thing here, it says the less electronegative atom is usually listed first. Well, we have not defined the word electronegativity. I'm going to give you the brief definition. Electronegativity is the tendency of an atom to pull electrons towards itself. So electronegativity is the tendency of an atom to pull electrons towards itself. We will find that some atoms are really good at pulling electrons towards itself, while others are not good at all. And we'll see that there is a periodic trend. So I'm going to go back to our periodic table, and I'm going to raise this up a little bit so we can get the whole periodic table in there. And we will find that the most electronegative, the meanest, baddest, most electronegative element on the whole periodic table is fluorine. Fluorine is very electronegative. Right behind it is oxygen, and then chlorine and nitrogen, and then it kind of tails off as we get further away from fluorine. Electronegativity increases as you go up and to the right towards fluorine. So the closer an atom is to fluorine, the more electronegative it's going to be. The further away it is from fluorine, then the less electronegative it's going to be. The most electronegative element is fluorine. If we say what's the least electronegative element, it's going to be down here, like cesium. Probably francium, but francium is radioactive, so we're going to ignore it. We'll say cesium. So electronegativity decreases as we go this way. And that's really all we need to know. We'll put the one that's further away from fluorine first, and then we'll put the one that is closer to fluorine second. We use prefixes, and the prefixes are listed over here, mono, di, tri. We'll go through those here in just a minute. We use prefixes to indicate the number of atoms of each element in the compound. And so, mono, di, tri. We do not use a mono if the first element only has one of those atoms. So for example, CO2 is carbon dioxide. We would not call it monocarbon dioxide. So don't ever start the name of the compound with mono. So we don't want to do monocarbon dioxide. The ending of the more electronegative element is going to be changed to ide. So oxygen becomes oxide, chlorine becomes chloride. Just like what we saw with the ionic compounds we saw a few minutes ago. Now, there's one other little detail here. If the prefix ends with an A or an O, and we've got a bunch of them over here, mono, tetra, penta, hexa, as we go down that list. If it ends with an A or an O, and the name of the element begins with a vowel, mostly oxygen, all right, then the two successive vowels are combined into one. So this is called dinitrogen pentoxide. You'll notice how the A on penta was dropped. So you wouldn't call it dinitrogen pentaoxide, you just call it dinitrogen pentoxide. Now, I am not going to test you on this on the test. However, you may see it show up on Mastering Chemistry. All right, I do like to show that the prefixes show up in common words that you see all over the place that are not necessarily related to chemistry, although some of the ones I'm going to show you are related to chemistry. Mono, which means one. For example, a monarchy is a single ruling body, like a king or a queen, whereas monochromatic is a one color. So monochromatic is one color. So my first computer monitor that I had when I was in college was monochromatic, and it was a hideous green color. Oh my goodness. All right, so it was monochromatic. Di means two. So dichotomy is something split in two. Diatomic is when we have two atoms in a molecule. I picked out a chemistry thing there. Tri, we see this one all over the place. Triangle has three angles. Trinity has three parts. Triplets, of course, there are three of them. Tetra, tetrad is something in four parts. A tetrahedron is a four-sided polyhedron. And Tetris, that game, that addictive game that I'm sure you guys have all played before, if you look at the little pieces, each one of the pieces has 4 squares in it. So next time you see that game, go Google a picture of it. You don't want to download it because you've got chemistry to study for. But it has 4 in it. That's where it gets its name. Penta. Penta means 5, so a pentagon is a 5-sided polyhedron, like the large building in large building in Virginia near Washington D.C. A pentagram is a 5-pointed star. Hexagon, so a hexagon is a 6-sided polyhedron. A hex wrench is an Allen wrench. In fact, I have one right here at my desk. I'm in my workshop. So here is a hex wrench right there. So you can see there's 6 sides on this. So that's a hex wrench. All right, we'll go back. A heptad is a 7-part ruling body. You don't run into that one very often. Heptarchy, that is I'm sorry, heptad is something in 7 parts. A heptarchy is a 7-part ruling body. And I don't know of any 7-part ruling bodies. I'm going to pause for a second. Okay, I just looked up heptarchy, and apparently it's a collective name applied to the 7 Anglo-Saxon kingdoms, and that was Northumbria, Mercia, East Anglia, Essex, Kent, Sussex, and Wessex. There you go. All right, I knew it had something to do with the English. All right, octa. So octagon, of course, 8-sided objects. Of course, October is the 8th month of the. Wait a minute. All right, you may be thinking October is not the 8th month; it's the 10th month of the year. Well, on the old Roman calendar, October was the 8th month of the year. September was the 7th month. October was the 8th month, November was the 9th month, and December was the 10th month of the year. And in that old Roman calendar, March was the 1st month of the year. And then they went about and invented January and February, and that fixed everything, I guess. Anyway, nonagon is a 9-sided polygon. Nonagenarian, if you have any relatives who are 90 years old or older, they are nonagenarians. Quite an accomplishment to make it to become a nonagenarian. Deca is 10. So a decathlon has 10 events. Decade has 10 years. Dodeca is 12. A dodecahedron is a 12-sided polyhedron. I just so happen to have a 12-sided polyhedron, a dodecahedron right here. All right, and so here it is. I designed this on the computer and printed it out on my 3D printer, and you can see it is a 12-sided object. 12-sided polyhedron. For those of you who are familiar with like role-playing games like Dungeons and Dragons, you're quite familiar with the 12-sided die. So, dodecaphonic. The dodecaphonic is a 12-part musical scale. Not very commonly used, but there you go. That's another example. Tetradeca, that's 14. And in case you're wondering, there is 11 is undeca and 13 is trisdeca, but 14, tetradeca. Tetradeca, I couldn't come up with another word that was, I looked, and so I just put tetradeca non-example. But you get the idea. You only have to know 1 through 10, and even then, you're probably not going to run into these. So let's go through the last few of these, and then we'll do the in-class assignment, and then we will declare victory over Chapter 2. All right, so we're going to practice naming these for non-metals. All right, CO. We're starting off with one that's simple. CO, that is carbon monoxide. Very easy. Next, CO2. Well, that one's carbon dioxide. CS2, that is carbon disulfide. Carbon disulfide. All right. CCl4. All right. CCl4. Well, that one is carbon tetrachloride. Carbon tetrachloride. Great solvent, but it's mostly banned because it causes cancer. Kind of nasty in that respect. All right, SO2, that one is sulfur dioxide. You know that odor when you light a match and you have burning sulfur? That's sulfur dioxide. All right, SO3, sulfur trioxide. Sulfur trioxide. SF6, sulfur hexafluoride. So sulfur hexafluoride. NO, nitrogen monoxide. Nitrogen monoxide. That's also nitric oxide, which is dangerous in high quantities, but it's actually an important neurotransmitter. Interesting. All right, NO2, nitrogen dioxide. That's that brown gas I showed you when I dissolved that penny in nitric acid. N2O, that is dinitrogen monoxide, also called nitrous oxide in an old naming system. And it is laughing gas. That is the same stuff as laughing gas. N2O3, so N2O3, that one is dinitrogen trioxide. So dinitrogen trioxide. And I don't know of any common uses for that. N2O5, that is dinitrogen pentoxide. If you take N2O5 and dissolve it in water, you will get nitric acid. And then PCl3, that is phosphorus trichloride. And then our final one is PCl5, and that is phosphorus pentachloride. So we're going to do our last problem, number 66, on the in-class assignment. All right. So most of these we saw already. So N2O, that one is dinitrogen monoxide. So dinitrogen monoxide, and it's also called nitrous oxide. And then here, NO, that is nitrogen monoxide. All right, NO2, that is nitrogen dioxide. N2O5, that is dinitrogen pentoxide. So dinitro, my N got a little weird there. So dinitrogen pentoxide. And then finally, N2O4, that one is dinitrogen tetroxide. And you'll notice that the A after the tetra was dropped and combined into just tetroxide. All right, and then if we go back to this, we will see that the next page is my favorite page of any page in each chapter. So that means we are done with chapter 2. Hurrah! Make sure you go back through this, and you will, if you go back through this and check your work and make sure that you get everything. If you have any questions, feel free to stop by my office hours. All right, have a good one.